Mike here with some latest tests on the ebulator, the whole refrigeration apparatus. First thing I'd like to mention is the sight glass. I did a previous video on a sight glass. It was a polyethylene, high-density polyethylene sight glass. Works pretty well. I was pretty happy with it. I was a little concerned about it blowing out, and I was pretty confident in it until the next day after I shut these valves down. Our compressor just died. Oh, yep. I'll discuss that here in a second. First I'm going to shut this fan off, kill it, and let it cool down here a second. So anyway, this sight glass, the next day I found that the high pressure that existed in there, because there was a saturated liquid in there that warmed up to room temperature, which was about 70 degrees in here, actually caused this thing to swell. It looks okay right now, but it was half-inch outside diameter, and it was probably 5/8. It looked pretty funny, so I hurried up and recovered the refrigerant, and I found this nylon tubing at a local Parker distributor. Just got 2 feet of it, and so I replaced the high-density polyethylene because the working pressure on this is 250 pounds per square inch, as opposed to the 100 that this was. So we'll wait and find out how much this thing's going to want to blow up on me, if at all, but I think it's going to be relatively safe. So I wanted to demonstrate something interesting I'd found. I'm going to go ahead and see if it'll start back up. There she goes. Okay. First thing I'm going to do is open my PXV a bit, let this thing get recharged with refrigerant, and increase the mass flow rate and allow the compressor to cool down. You see these last two values here. This is our suction temperature. That's actually measuring the refrigerant right after the PXV, and this is the superheat coming back to the compressor. You can see it rapidly falling, really rapidly falling, and that's going to approach the suction temperature. The way this thing operates, there shouldn't be an extreme amount of superheat except in some certain conditions, which is why this thing just shut down. I'll talk about that here. This other value here at the top is the discharge temperature off the compressor. It's still pretty warm. It's climbing. The compressor's making some funky noises, but hopefully that actually starts to level out and fall as it starts to get some cool refrigerant coming back to it. Yeah, that sucker's pretty warm. So I missed my window there to demonstrate the overloaded condition this was in. But in the meantime, while the thing evens out, I'll mention the pneumatic expansion valve. Talked about this previously, and kind of have this thing finally dialed in to the point where it's relatively easy to control. So all I'm doing is applying air pressure to the power head on this TXV, and I have the superheat adjusted just so there's probably about 5 pounds of pressure that the superheat spring is applying towards the needle. So you can see about 65 pounds here, and we have actually probably around 65 pounds up here on our suction. Now what I noticed here previously when I was playing around with it is usually about whatever setting I have here, the suction pressure would be about 5 pounds higher than that. She's evening out here a little bit. I don't know if you can make out the refrigerant in there. This nylon's a little cloudy, so it's natural colored. So it's kind of hard to make out in the video, but see how we're doing here. So we have what, about 1.5 degrees of superheat on the suction, and our discharge temperature is falling as I expected. Second number there is subcool temperature after the air heat exchanger condenser. Now, what I actually wanted to discuss was the need for a float as a refrigerant control in the ebulator. Because this thing gets filled full of liquid refrigerant, if the TXV is closed down in such a way that the refrigerant in here is being evaporated faster than it's being supplied, it'll get starved just like a dry type evaporator, so that the liquid may only be up to a level of here or here or so, and the remaining gases that are formed and travel up through these pipes get superheated, causing excessive amounts of superheat. I had 60-some, well, probably 50 degrees or so of superheat, which caused the compression to be far, far greater than adiabatic, than isentropic, and what I ended up with was excessive amounts of superheat on the discharge. Compressor starts to get very hot, and eventually it just shuts off. So we're starting to see things starting to level off here a little bit, and I'll give it a second here until I adjust the pressure. So now we're still at about 65 pounds there, and surprisingly we're right around 64-65 pounds on the suction. It's a little unusual from what I've seen, but we'll go ahead and we'll drop the pressure on the power head at around 50 pounds, and you can see the suction temperature starts to fall. Now this is all, of course, dependent on the load. We really drop her off to the point where we start to starve this thing again. These coils are going to start to freeze up, starting at the bottom mostly. And you see the suction start to fall. Now it's not going to fall rapidly because, well, for one thing, the large amount of liquid propane inside these coils needs to be cooled down as well. Then the copper needs to be cooled down, the water on the surface of the copper needs to be cooled down, and then the air in the immediate vicinity needs to be cooled down as well. So eventually it will cool itself down, and of course if I had this thing inside of an insulated box or refrigerator or something, this would happen a little more rapidly, especially if the surrounding air was already fairly chilled. Feel it starting to be pretty cool. We're down around 30 pounds there, and just under 50 pounds on the suction, which is about 28 degrees Fahrenheit. Now, this is something else that's a little bit unusual. Pressure is still dropping, but the temperature on the suction temperature, really the low pressure liquid temperature, I've found in the last few runs of this machine are a good bit lower than the corresponding pressures, and I'm starting to believe that the way in which I've been charging as gas, I've been getting some, what used to be called non-condensable gas, basically air, is ending up in the system and showing higher pressure readings than the temperatures would indicate. I haven't gotten to the bottom of that yet. Maybe I got a different batch of propane, but it's a little different than what I've seen before. At times I'll even see the superheat temperature, the discharge of the compressor, even be higher than what my corresponding, lower than my corresponding condenser pressure would indicate, which doesn't really make any sense at all. That, I think, would also indicate that there's air in the system. So we can see our suction pressure has finally dropped to within about 7 pounds, 5 or 6 pounds perhaps. And you see the coils are starting to freeze up again. Now, what happens if I turn this fan on here, which is blowing air directly across? It's rather warm in here, it's 95 degrees or so. Now we're putting some air across these coils. Now you can see the pressure starting to rise. It's greater heat load. The refrigerant is boiling away more rapidly, and the pressure rises. So as the pressure rises, the rate of evaporation will fall, but as more heat is applied to it, that rate of evaporation continues, and these two principles seem to kind of fight each other a bit. You can already see, as the pressure rises and the temperature inside is rising, it's starting to defrost a little bit. And that's a little bit from my hand over there, but on the other side you can see some more or less bare copper. Now, as the PXV is still starving, they're still in a condition where it's admitting less refrigerant for a suction pressure corresponding closely to 30 pounds, we are in a starving condition. We're starting to starve this thing out, and as heat's passing across these coils, you can see the very top coils are starting to actually fall out. Take a look at our superheat. Right there we can already see 23 degrees Fahrenheit is basically what's coming out of the PXV or PXV, and we've got 8 degrees or so, a little more, of superheat. See that superheat starting to rise. Now, I wish I had a live graph of this stuff, but what will happen is the discharge, that very top number, is going to start to increase as well. The efficiency of the compression is decreasing. The amount of superheat on the suction it may be useful cooling, but in terms of compression, it's not very efficient for compression. What you end up with is a less dense gas, and the volumetric efficiency starts to go to hell. So the amount of the actual mass flow rate starts to decrease, and the amount of discharge superheat increases, which is taking up more space in the condenser surface area to exchange heat, and will reduce the amount of subcooling, so that second number may actually begin to rise. Yeah, 42 degrees. So as it continues to rise, eventually that discharge temperature is going to really start to rise. The compressor will get very hot and it's going to cut out. So I think this really just indicates the importance of having a float control that actually regulates the level of refrigerant in here, rather than simply the pressure that the ebulator actually. It's starting to go pretty rapidly now. Rather than the pressure that the low side operates at. And we shut the water or the air down, so the heat load is reduced. There's less air moving across it, so the suction temperature starts to fall. And it'll start to freeze up again. So superheat's probably going to start to fall. 43 degrees now, 42.6, 42.3, and on down. The first value there, again, the compressor discharge, will lag behind a little bit, but it'll probably stop rising, level off, and then begin to fall as more actual cooler vapor really, is drawn back to compressor, which helps to keep it cool. Should hopefully lead to higher volumetric efficiency and higher compressor efficiency overall. Greater mass flow rate, on and on and on. The other problem with high discharge temperature is that's less capacity that the condenser actually has to remove heat, and correspondingly the pressure will also have to rise as well, which also, because your compression ratio increases, so the amount of actual work that the compressor has to do increases. So the amount of electricity you consume for a certain amount of cooling, it starts to go to hell. So slowly, suction superheat is falling. The discharge temperature is falling, and the subcooling temperature is falling. More or less. See things frosting over a bit. So, now that we're kind of back at a normal state, about 33 pounds, about 31 pounds, go ahead and increase pressure. I don't know how much air I have left in my tank. Take her up to 50 pounds. And the suction starts to rise. So we're actually admitting more refrigerant. Make out a little bit of the bubbles going on there. Things start to get a little more violent. The overall liquid level starts to rise. Now, ultimately, what I'd like to do with this, actually the ebulator itself, this first model, is probably going to get retired possibly this weekend. and I'm going to switch over to an evaporator, air exchanger, evaporator, similar fin construction, similar to the condenser. It's actually going to be the actual evaporator that came out of the air conditioner that both that condenser and that compressor came out of, which is this small unit encased in the styrofoam there. I'm going to modify the copper lines on the end, unbraze several of the lines on the end, the little U-tubes that connect everything, and give it more or less 1 or 2 runs for a dry type evaporator. And I'm going to construct a vertical copper column that they'll tie into and feed this thing as a flooded evaporator, a wet evaporator. But a few different things I'm going to do is I'm going to try to maintain the liquid level, even the resting liquid level, higher than the top coils, which I haven't really done and haven't really designed into this particular unit here. The other interesting issue with trying to do that is I can't fluctuate the pressures as wildly, because I always have to wonder or risk sending too much refrigerant in here and actually getting it up to the suction and slugging back. It's kind of the cool thing about the gravity flooded evaporator is that, similar to a TXV or a thermostatically controlled, a superheat controlled evaporator, the amount of delta T, the temperature that this thing, the coil exists compared to the environment, the heat load, say the fan or something like that, the air passing across it, the delta T is kind of self-dictated in a TXV based on the amount of the temperature of the suction. That essentially that capillary, or that bulb that would have been on that TXV, more or less measuring the temperature of the suction, and to determine how dry that suction is, and how much, if the refrigerant needs added to the line, or needs to close down. Should quit droning on so long. I'm just rambling. But with the flooded evaporator, it's also kind of a self-selecting, self-regulating system, depending on the heat load. If I add more heat, say with the fan, and blow it across the coil, ebullition becomes more violent, vapors are produced more rapidly, and are carried back to the compressor, requiring the TXV to admit more refrigerant. Conversely, if I reduce the heat load, the ebullition starts to fall, and the vapor is being produced less rapidly, being drawn back to the compressor less rapidly. And if my refrigerant control continues to admit refrigerant to it too much, eventually the liquid level is going to rise too high. In addition, the suction pressure is going to start rising to the point where the delta T is reduced. So it needs to be closed down a little bit in order to get that amount of vapor produced to be equal in mass to the amount of liquid that's being admitted to it. It's really quite simple. It's just a matter of regulating the liquid level in the thing, and as long as it's regulated at a certain height, say above these coils, a natural thermosiphoning effect occurs, which can actually be seen in this sight glass. And that effect I could probably reduce by insulating these lines a little bit, because they're of course absorbing heat from the environment and causing vapor to be produced, having it bubble up through. So we're at about 52 pounds on the PXV, about 55 pounds on the suction. And we have a pretty small amount of superheat between these two values here. Pretty small difference. Much smaller than you would probably see with a conventional superheat controlled TXV. Our discharge temperature is coming down to something reasonable there. Not too high. We're showing about 98.6 degrees on the subcooling temperature, and our pressure would indicate for pure propane at about 205 pounds per square inch would indicate about 112 degrees condenser temperature, which is probably a little bit high considering that our discharge over compressor is at 120 1213. So anyway, be surprised if anybody actually sat through this whole video, because I just keep droning on and rambling, but I'm also doing it for my own use, just to kind of log as I go along. And, you know, as I'm sure you can tell, I don't exactly understand everything that I'm looking at or that I'm working with. It's just an ongoing process. But I am pretty pleased with the PXV, how it's working out, and I hope to further experiment with it and eventually try to adapt a thermostatic expansion valve to operate as an automatic float. And how I'm going to go about that, I won't explain right now, but I have some ideas that I think are worth investigating. Because in order to control the liquid level in this, you know, conventionally you would have a large mechanical float inside of some kind of a tank, a header that has a removable plate for, you know, inspection, repair, and all that kind of stuff. And it gets rather complex. The other issue is trying to make a mechanical float that can operate between, you know, relatively large pressures. We're not talking about a little water float inside of a toilet tank that's only trying to hold back 60 pounds per square inch. You know, you could be talking about 200 pounds per square inch of difference, and it needs to work. It needs to be reliable, and then of course the other issue is the fact that the propane liquid is far less dense than liquid water. It could be very turbulent in there if it's not insulated real well. I have a lot of vapor bubbles and stuff, a lot of rolling around. The materials that you select to actually make the float, you have to be careful about that, of course. Can't just use any old plastic or anything. It probably should be a thin-walled metal ball or tube of some sort. So some issues I'm going to have to address. But nonetheless, I think I better wrap this thing up right now. Just take one last look. Yeah, it's reasonable, you know. It's moving some heat, probably not a great deal. Of course, I should have this thing inside of a box or something like that, but just fooling around right now, getting to know it, beating the shit out of it, just for shits and giggles. Let's go ahead and just drop the pressure off. Hell, let's just drop it down to nothing. 0 pounds gauge. We're starving it. Yeah. Have a great day. Thanks.